Hello, everybody. Can everybody hear me okay? Um, let's get started. Hello, for those who don't know me, I'm Raymond. I am a chemistry tutor. I have decided to Sorry. Um, yes, so I'm running these live streams just to help with trial revision. I know some people are already having their trials today, so if you can't join us, that's okay. I'm sure you guys will be watching this in at a later time. So we're gonna get into it. I do encourage people to leave questions if you guys have any. So feel free to type in the comments if you do have any questions. If you don't have questions, I'll just keep going. So I do strongly recommend questions to be there. I'll answer to every one of those. So don't be too shy. I believe you might be able to leave an anonymous comment. If you can't, don't worry. I'll make sure these comments are not released once this live view goes on. And then, yeah, we'll get started. So, oh, chat is disabled. That's a good. Let's open chat up. Goodbye. Update. Is it because? Ah, okay. No, it's not made for kids. Let's refresh that. Great, we have chat. Beautiful. Okay. Lovely. Let's get started. So the objectives today is the objectives are to go through all the different types of questions that you get in Mod 5 to Mod 8. Have an understanding of how to do those questions, how to answer them, what's required, what are the working outs, various steps to get to your answer. So we'll do a range of multiple choice questions to short response questions. Again, if you have any questions, please leave them in the comments and I will have a look and answer them once I see them in the chat. Hello, please feel free to ask any questions below. Great, okay, let's get started. So, phosphorus pentachloride gas undergoes an equilibrium with phosphorus trichloride and chlorine gas according to the following equation. 0.2 moles of phosphorus pentachloride was placed in a sealed 2-liter container so that the equilibrium could be achieved. The container was found to hold 0.15 moles of chlorine gas. What is the equilibrium value K for this reaction? All right, so this is a very simple ice table question. So there's two types of questions with these equilibrium ones. So I'll go for a little bit of the theory as well, so you understand what types of questions you might get. So there's two types of questions. So just as a side note here, we call these type 2 questions. So your type 2 questions are where you've got an initial amount of reactant, and then they also give you the equilibrium concentration or amount for your product or of a reactant. We then need to use the ice table to work out our equilibrium concentrations, and then we plug it into our KEQ expression. Now, as a side note on a type 1 question, those are your most straightforward questions where you get given all your concentrations of your at equilibrium. You can plug those straight into your equilibrium expression to work out your equilibrium value constant. So with these types of questions, we want to look at, or we want to try to find the numbers that we're going to use in our calculation. So we get given an initial amount of phosphorus pentachloride as our reactant. If we're getting given moles or some sort of amount, we need to make sure we have a volume so that we can work out the concentration. So we've got a volume there of 2 liters, beautiful. And we've got a container that subsequently that holds 0.15 moles of chlorine gas. We're going to assume that to be our equilibrium concentration. Yes. Great. So, sorry, got distracted. So first thing you want to do is your equation. So they've already provided that to you, so beautiful. No need to stress about that. If they don't give it to you, make sure you have a balanced equation based on what the question has provided you. Second thing we want to do, we want to write out the KEQ expression or the equilibrium expression. So generally speaking, we want to do the product of the product concentrations to whatever coefficient of the product in the equation coefficients are. So for example, these are all 1, 1, 1. So they're going to be to the power of 1. And that's going to be over the product concentrations, the products of the concentrations of the reactants to the power of whatever the reactants coefficients are as well. So that's a general equation for it. If we want to work out the expression for this particular reaction, we do products over reactants. So that's going to be PCl3 concentration of Cl2 over the concentration of PCl5. Now I note that the concentrations are of at equilibrium. Okay. Now, how do we get to these equilibrium concentrations? Great. We now do ice table. So I'm going to do an ice table on the side here. Now, some schools have learnt rice. I'll do rice, but do note that it is optional. RICE. Just for color's sake, R is ratio. Ratio is the coefficients of the equations. So in this case, they're all 1, 1, 1. I stands for initial, and this is the initial concentration, okay? The square brackets meaning concentration. So the initial concentration, C stands for change. So in the equilibrium, how much of this particular material has undergone the change? I'll talk about that a little bit more later. And E stands for equilibrium. And this is the equilibrium concentration, okay? So coming back to our table, our initial amount is given by 0.2 moles. In this ice table, we want to make sure we're doing concentration. So we want to do 0.2 over 2. That's our concentration, which equals to 0.1. PCl3 Cl2, the product, so initially they have a concentration of 0 because they haven't been formed yet. We're talking about at the point that I've just added in PCl5 into the reaction vessel, what are the concentrations? Now, when they undergo change, our reactants are going to get consumed, our products are going to get produced. So in terms of a variable of how much they undergo, this is a variable we're trying to work out. We typically denote this variable to be x. And now this is where we utilize two pieces of information. First piece of information is the ratio. If it's 1, we would just denote 1 times of this variable, and we're going to call this variable x. If it's a reactant, they're going to get consumed, so it's going to be negative x. If it's a product, they're going to be positive. And because they're a ratio of 1 also, they're going to be positive x, positive x. Now, our equilibrium is just going to be our initial amount plus our change. It's very important that you denote the sign, if it's positive or if it's negative, in your change, so that you can just do this. 0.1 minus x plus x plus x. So now we've got our equilibrium concentrations in terms of x, of course, we will work that out. We can then put it back into our equation here and denote everything based on x's instead of it being all in concentrations at equilibrium. So in this particular case, that would be x times x over 0.1 minus x. Now, there was another piece of information we hadn't used yet. This 0.15. This 0.15 is the equilibrium concentration of our chlorine gas. Oh, what happened there? Oh, everything's been shifted by something. So, my apologies. Let's redo those ones. 1, 1, 1, 0.2 over 2, 0, 0, minus x, 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 0.1 minus x, x, and x. So, the equilibrium concentration of our Cl2 is 0.15 over 2, which is 0.075. Now, we can sub that into our x and we can get a KEQ expression. KEQ value. So that's 0.075 times 0.075 over 0.1 minus 0.075. And we get to calculate a value of 0.225. And that equals to A. Cool? Any questions? For those 2 people watching, thank you. If you happen to be my favorite tutoring students, please say hi so I know you're here. If not, that's okay. You can also put your name as well. I will be very delightful to know who's actually attended to this live, and I very much appreciate it. Okay. No one has any questions? We will continue. Thank you. So, question 23. Methanol can be produced by reaction of gases, carbon monoxide and hydrogen according to the equation blah. It's exothermic. The graph shows the results of an experiment when CO and H2 gas were added to a 10-liter vessel at a temperature of 500 degrees. Now, I didn't mention this for the first question, but most of my questions will have a reference down below where the question was derived from, whether it was basically where the question was derived from the school, the year, the paper type, the age of the paper, what question type, and a reference. Now, don't worry about this reference. This is a personal reference for my tutoring. Reference to the syllabus, that is. If you guys have any questions to that, let me know. More than delighted to answer to that comment. All right, back to the question. So we get given a graph, and the graph is in moles of reactants and products. So when we look at these graphs, different variations of questions you can get asked for this. You can get asked to draw it. You can get asked to calculate equilibrium constant like this one. You can get asked to denote what might be happening based on the Chatelier's principle. But for the purposes of today's stream, we are just going to be focusing on calculations. So this question is asking, what is the value of the equilibrium constant for the reaction under the above conditions? So interpreting these graphs, we can see that initially at time equals to 0, they've got certain concentrations. It seems like, sorry, there's a missing arrow here. My apologies for that. So it seems like your reactants have just been added into your reaction vessel. There's no products being formed yet, but over time, we can see our reactant concentrations decreasing and our product concentration increasing. So we can use that information to calculate where that plateau happens is where the equilibrium occurs, and we can use those equilibrium amounts in moles to calculate our equilibrium constant. So let's have a look. First thing, let's write an equilibrium expression for this. So I'm just going to take 2 lines. Because I have fat handwriting. So an expression would be our products over our reactants. Now I note that our coefficient for hydrogen, H2, is 2. So we do to the power of 2. Okay. Now they're all over 10 liters as the volume, and these are moles. And we can remember that C equals to N over V. You could calculate each individually, the concentrations, but given I don't have much room in this particular question, I will just work them out in one line and put them all in the calculator in one go. So our concentration of our CH3OH, our methanol, is 0.1 moles. So that's 0.1 over 10. Our CO equilibrium concentration, equilibrium amount is 1 mole, sorry. 1 over 10. And then our H2 is 0.9. So that's 0.9 over 10 squared. So let's see what that calculator value comes to be. So that comes to be 12.3456791 ... Now, because K is a constant, K doesn't have any units. But when we do any calculation questions, we need to remember 2 things. Okay, I will reiterate this a lot. So first of all, in any calculation question, we want to have units and number of sig figs. Sig fig stands for significant figures. You will get marked wrong if you don't have either of these as your final answer. So only put these as the final answer. So you do all your working out, lay it all out. You get to a unrounded calculator value like I have here, and then you would go and do the rounding of the significant figures, including of your units. So in this particular case, we have to look at the numbers that we've used and look at how many significant figures they are. So just to denote that, this is 2 sig figs, 10 is 2 sig figs, 10.0 is 3 sig figs, but we're not dealing with 10.0. We've used 1.0, 0.9, 0.1. Those are 1 sig fig. Sorry. Those are 1 sig fig, yep. When we get to 1.0, 1.0 is 2 sig fig. We never round to 1 sig fig. The lowest we round to is 2 sig fig. So what we have as our answer is 12.12. That's it. 12 and 2 sig figs. Okay. Okay. Should be pretty straightforward. If anyone has questions, fire away. Oops. Okay. Moving on. Now we get to our next set of questions, which are solubility. So this is KSP. Now we're trying to work out, so the molar solubility of barium phosphate is 1.3 times 10 to the negative 5 moles per liter in pure water. Calculate the KSP value for barium phosphate at this temperature. So, if you didn't know already, the KSP values for most of your insoluble salts are provided on your data sheet on the bottom on the from the first third to the bottom of the first page. Those all have your KSP values. So, but those KSP values are to 25 degrees. This is why you can't use that data for this question, because this question is asking for 30 degrees. So what do we do? Very simple. So we first, for any question, again, we always start with equation. So what is our equation? Equation for the solubility or the ionization of our barium phosphate. So we do this, barium 3, PO4, solid, gives you 3 barium ions. Barium is 2+. Now phosphate, there's 2 of those, and phosphate is 3-. If you don't remember these, I strongly recommend you remember these. This is assumed knowledge from year 11, unfortunately, so don't miss out. Don't forget. Okay, so we want to generate our KSP expression. KSP expression, now, how we denote a KQ expression is products over reactants. However, we disregard this bottom one because it's a solid. Solids don't have concentrations. So what we're left with is just the top, or more simply, it's the ions product. We sometimes denote these to be IP or ionic product, but remember for KSP, these are all at equilibrium. Whereas when we're dealing with ionic product, which we'll calculate, it deals with concentrations at any point in time. Okay, that's something we'll deal with later, so don't stress about it at this current moment. Okay, now this long-winded way to attack this question, there is a shortcut. I'll go through the long-winded way and show you all the little tips, but I think I will do an extra page just to show you all the different varieties of it. Yes, let's do that, because I feel like that will be very handy for people. Okay, so long-winded way is to do an ice table. So not worrying about the salt there, as in the solid. RICE. Ratio is 3, 2. Initial 0, 0. Change. Now, again, these are products, so we do positive, and based on the ratios, we do 3 times a variable, which is x. Or for those who like to use, oh, why is it not going away? For those who likes to use, there we go. For those who likes to use solubility, we like to use S, and in this case, we do 3S and plus 2S respectively. So our equilibrium concentration is 0 plus 3S for barium, 0 plus 2S for phosphate. So that's that. Now, subbing it back into our KSP, KSP is equal to 3S whole cubed, 2S whole squared. That happens to be 27 times 4, 108. 108 times S to the power of 5. Now our S just stands for solubility. The reason why that is what this is saying is for every 1 liter of solution, it can dissolve 1.3 times 10 to the negative 5 moles of barium 3 phosphate. So that means if that dissolves, we can assume that there's going to be an equal amount or a molar ratio amount of barium and a molar ratio amount of our phosphate. Okay? So that's why we can say for every 1 mole or for every 1 solubility amount of our salt, we can get 3s and 2s amounts of barium and phosphate respectively. So putting that in our calculator, we get -5 to the power of 5. Ooh. So we get 108 times 10, 1.3 times 10 to the -5. Yep, 4.009966 or 644 times 10 to the -23. Again, no units. This calculator value, put it all in there now. We come and round based on the lower sig fig used. So we used 1.3 times 10 to the -5, which is 2 sig figs. So in our answer, we want to round to 2 sig figs. So that will be 4.0 times 10 to the -23, 2SF. Cool. Any questions? Quick drink break. So again, these will be available to you as a file in the bottom of the description. So you can always reference back to these instead of the video if you choose to. Okay, next question. 25. Predict whether a precipitate will form when 0.001 grams of silver carbonate is added to 100 mils of water. Okay, so these types of questions, how you attack it is as follows. So you want to consider the ionic product. So the ionic product is just your ion concentrations at any point in time. Find the concentrations, multiply together, get a value, and then you want to compare that compared with KSP. I like to visualize KSP. This applies to KQ as well. The KQ aspect is finding Q. So if I was writing this upside down for someone, for my student yesterday, and I messed it up. So I'm writing it in the right way, so I have no excuse to making it wrong. So when I consider this, I want to consider my ionic product. If it's less than KSP, then I have soluble salts, or the amount of salt added is soluble. If my IP is greater than KSP, then a precipitate is going to form. Okay. If it's greater than your KSP, precipitate. If it's less than your KSP, it's soluble. And if it's at your KSP, run out of space to write this, we have saturation. Or we can say this solution is saturated. Great. Let's start the question. So, firstly, equation. So this equation is your solid salt, Ag2CO3. Ag is +1, CO3 is 2 negative. So we do Ag2, CO3, solid gives you 2 Ag plus aqueous and CO3 2 minus. Okay. KSP expression. I'm going to write KSP expression. Okay. Actually, let's not. Let's write ionic product. So IP stands for ionic product. Should have mentioned that earlier. Hey. Ag plus squared, CO3 2 minus to the power of 1. Great. Now, how do we find these concentrations from an amount of salt that's been added? We don't know the solubility, That's fine. We've got an amount. We can work out if that amount will be greater, if that amount will cause the ionic product to be greater than the KSP value. So let's consider what we've got. We've got a mass value and the mass of silver carbonate. So we can work out the moles of Ag2CO3 by simply mass over molar mass, which is 0.0010 grams over the molar mass of silver carbonate. So I know the mass of silver carbonate. I'll write it out now, 107.9. But if you forget, how do you find it? Good question. So you get given this on the data sheet, so there's no excuse. It's given to you, but because I don't have it physically with me, so I can search it online. So it's here. So silver is atomic number 47, 107.9. Now, I'm sure you know the molar mass for the other two atoms, so I'm not going to check the data, not checking the periodic table. If you do need to check, that's okay. No one's judging you, but I'm hopeful that you've practiced enough questions that you can memorize those two elemental molecular atomic masses off by heart. So we've got carbon 12.01 plus 16 times 3. And common question I get is, what's the molecular mass units? Grams per mole. So thinking back, how we derive this, the grams cancel and the moles come back on the top, and you should get a unit of moles. So putting this all onto a calculator, let's have a look what we get. 0.001 over 107.9 plus 12.01 plus 16 times 3. So I always recommend putting it into a scientific notation because it's easier to round your significant figures later. And it's also easier to write rather than writing all your zeros out. So 5.9555714 ... times 10 to the negative 6 moles. Now, going back to year 11 mole questions, we want to relate our salt to our Ag and to our CO3. Similar to doing your ice table. That's the whole concept of ice tables. It's molar ratios, all of that stuff. So we want to relate this amount to our Ag and to our CO3. So if we compare the molar ratio of Ag, which is 1, Ag2CO3, which is 1, and Ag plus, that's 1 to 2. So what we can say is the moles of Ag is equal to 2 times moles of Ag2CO3. Now, make sure you justify why. So we can say 1 to 2 molar ratio, and we can say Ag2CO3 ... Ag plus. Okay, simple enough. Oh, sorry, I left ratio out there. So that's going to equal to 2 times the answer, which is 1.19. Yeah, 1.199111428 7 times 10 to the negative 5 moles. And also the moles of our CO3 2 minus is equal to just the moles of our Ag2CO3, because 1 to 1 molar ratio, Ag2CO3 to CO3 2 minus. Okay, so we've got that. And I need some more space. Perfect. Alrighty, so we've got moles. How do we get concentration? So again, a note, C equals N over V. So the concentration glad I put this to a new page. Concentration of Ag plus is 1.1911428 times 10 to the negative 5 moles over the volume, which is 100 mils. We do 100 mils as liters. That will give us 1.1911111 times 10 to the negative 4 moles per liter. And then our concentration of our carbonate is 5.955 times 10 to the negative 6 over 0.1 liters. That's just going to be 5.9555 times 10 to the negative 5 moles per liter. So we go back to our ionic product and we say, okay, this is the expression. Sub the numbers in. Now, I like to write out all my working out. I strongly recommend that everyone does that as well. The reason is, it's such a common mistake to just forget to carry forward an error. There are no pity marks in HSC/trials, unfortunately, unless your school does. Generally speaking, there's no pity marks. You get it right or wrong. So if you write out all you're working out, when you're checking your answers, you go through and you check, oh, actually, I've actually calculated the wrong value. I can just retype this calculated value in there. I don't need to go back and do all my working out again just to come back to this particular spot. By having all your numbers there, it saves you so much time. You might waste a little bit of time at this particular point when you're working out the question, what your actual answer is, but looking back at it, you're going to save so much time. Now, because we've done so many lines of working out, you might lose your calculator value, which is why I strongly recommend you write out your full amount, or for at least 5 to 6 digits of numbers or significant figures of numbers. That way, when you put it back into your calculator, you won't lose it. Or you do the safe way. You store your numbers. I will show that trick to you guys another day. But I think storing your number takes up too much time, so don't worry about that. Make sure you've got these numbers written down. It'll save you so much time. You won't make a mistake. If you make a mistake, you can always check back on it. Okay, enough rambling. Let's calculate this answer. 55714 times 10 to the negative 6. 5. Okay, so I got 8.449688568 times 10 to the negative 13. Just for safety's sake, we will put this into the calculator again. Great, got the same answer. Now, is this bigger than your KSP value? So we've done that, we've done this, we've done that. Now we need to compare our KSP value. Again, KSP value, where do we get that? It's on our data sheet. Let's rotate this bad boy. Okay, what are we looking at? We are looking at silver carbonate. So it's 8.46 times 10 to the negative 12. So is this greater or less than 8.46 times 10 to the negative 12? So we have the bigger the negative number, the smaller the actual number is. So this is still less than your KSP value. So because as your ionic product is less than your KSP value, therefore no precipitate forms. Okay, Any questions? Leave them behind. Not sorry. Take that back. Not leave them behind. Leave them in the chat. Happy to answer them. Otherwise, I would assume that everything's going all right and people are making sense of what's going on. All right. Moving on. Which of the following metal carbonates have the highest solubility? Okay. I will have to split screen for this one because of this. I need to see the KSP value. So, oh, I totally forgot. Why did I enter some more space above? Okay. So, bit of a sidetrack. Let's come back to this question. We've identified a cheat, a hack to identify the KSP value based on your solubility. Give you another example to kind of visualize what's going on. So, let's do AgCl, right? AgCl are monatomic. Our KSP value, based on this sort of relationship, if we do an ice table, what we will get is S times S, which is S squared. Oops. Which is S squared. This is for monatomic. Let's say you have that comes from, sorry, let's write all this out. So because I have this equation, I get these expressions. Yeah, I'll write one more. Let's go. I love using silver, so I hope I haven't offended anyone by using silver all the time. Okay, that's not. Okay. Bit of space. Okay. Oh. You know what? That's fine. Take that. All right. So our KSP value for our calcium hydroxide is going to be S, because that's 1, and times 2S whole squared, because this will be 2. See the coefficient there? So for our salts, which are where there's only 1, and then there's 2 of these, what you'll get is S times 4S squared, which will be 4S cubed. All right. Another example is where you got a mono cation and then sorry, my apologies, not mono cation. We've got a trication and we've got a mono anion. So what do we get? We get Ag plus or cubed plus PO4 3 minus. Based on S, this will be 3S cubed plus, times S. So that's going to be 27S to the power 4. So when you do these kind of questions, you can always generalize them based on how they dissociate. And make sure first you've got a correct KEQ. Sorry, not KEQ. You've got a correct KSP expression. And then you look at your equation to determine the coefficients. And then the third step is to do your S or 2S or 3S based on your expressions. Okay. All right. Going back. Okay. This question involves KSP values. Now, in light of what we just did, we can answer this question. So generalizing what the KSP expression will be in terms of their solubility, how do we do that? So just to note, calcium carbonate is CaCO3, copper carbonate is CuCO3, iron 2 carbonate is FeCO3, lead 2 carbonate is PbCO3. So as you can see, there's only one cation, one anion. So our KSP value or KSP expression for all of them is just going to be S times S squared. Okay. A lot of people will spend a lot of time on this, going from KSP value. Oh crap, what's the solubility going to be? What we can do is visualize this. If KSP is high, then solubility is going to be high. Why? Let's say your KSP value is 10,000. Sorry, let's use 100. Make maths a little bit easier. If we do this square root of that, because S is just KSP square root of KSP, we do square root of 1000 as opposed to 100. What's your number going to be? I've used a completely bad number, but square root of 1000 is 31. Square root of 100 is 10. So this is KSP, this is S. The higher the KSP value, the higher the solubility. So we can look at our KSP data sheets and see which one has the highest KSP value, and then that will denote the highest solubility. So let's have a look. Calcium carbonate, 3.36 times 10 to the negative 9. Copper 2 carbonate, 1.4 times 10 to the negative 10. Iron 2 carbonate, 3.3 times 10 to the negative 10. Oh, 11, sorry. Lead 2 carbonate, 7.4 times 10 to the negative 14. So again, higher the negative power, lower the number. So the lowest number is your lead 2 carbonate, so that's out of the picture. Our highest number will be A, because it's got negative 9. Negative 9 is higher. Okay. Okay, moving on. These are our mixing solutions. Again, we want to try to identify the ionic product and then compare that to our KSP. Very similar to the question that we did 2 questions ago. This one. Now back to the full page for now. So firstly, equation. Let's do a chemical equation. Now you can skip the full equation because you're going to get spectator ions. What are spectator ions? Ions that's not participating in the actual reaction. So this reaction is a precipitation reaction. All that's participating are 2 things, the Ag and the Cr. Now, if you've forgotten why those 2 things form a precipitate, we should revisit our SNAP. Sorry, I've lost track of that. So SNAP is always soluble, okay? Always soluble. SNAP stands for ions which are always soluble, and it's an acronym. Sodium for S, nitrate for N, ammonium, acetate, and not phosphate, not phosphorus, potassium. So these ions are always going to be soluble, okay? So we can see our nitrate there, soluble, sodium, soluble. So those are the Ag and Cl are the only two ions that's going to form a precipitate. So similar to what we did in the previous question, we want to try to find we want to first agree on the expression. That's just going to be Ag plus and Cl minus. We want to identify the moles of our silver and chloride, subsequently find the concentration. So let's do Ag first. Ag plus is going to equal to the moles of our AgNO3 because of 1:1 molar ratio. Which will be 0.01 liters times 0.01 molar, sorry. That will be 1.1 times 10 to the negative 4 moles. Yep. Moles of Cl minus is going to be moles of NaCl. Again, 1:1 molar ratio. And NaCl to Cl minus, which is 0.01 liters times 0.0001 molar. Oops, that will be 1 times 10 to the negative 6 moles. Now, concentration. We've got a combined volume of 20 mils, so that's the volume that we're going to be using. So that will be 1 times 10 to the negative 4 moles per 0.02 liters. 1 times 4 over 0.02, 0.005 moles per liter. Concentration, bless you. Concentration of Cl minus is 1 times 10 to the negative 6 moles over 0.02 liters. Oops, 1 times 10 to the negative 6 over 0.02. 5 times 10 to the negative 5 moles per liter. Our ionic product is going to be that 0.005. Let's omit the units here, times 5 times 10 to the negative 5, which is 2.5 times 10 to the negative 7. And looking back at our KSP values for silver chloride, 1.77 times 10 to the negative 7. Now that's greater than 1.77 times 10 to the negative 10, which is equal to our KSP. Since IP greater than KSP, therefore precipitate will form. Sure? Great. Lovely. Hope everyone's doing okay. Now, those are all the Mod 5 questions. I have noticed that I have not done a Gibbs free energy and a common ion effect. So if we have time at the end, I will do those two. Common ion, Gibbs free energy. Great. Okay, we start the Mod 6 calculation questions. We start looking at enthalpy of neutralization first. So neutralization reactions are exothermic. Exothermic as in delta H is less than 0. We use two equations here. We use Q equals to MCAT. We use delta H is equal to negative Q on N. Now, things to note. Our moles is the moles of water, contrary to what we learned as enthalpy of combustion. Our mass is our mass of water, or the mass of the solutions, two solutions added together, and we assume a density of 1. Our C, which is 4.18 kilojoules per kilograms per Kelvin, excuse me, that's on the data sheet. And delta T is the temperature change. So T final minus T initial. The Q on the top comes to the bottom. Cool. So first thing, you guessed it, equation. Let's do an equation first. So we do NaH aqueous plus H2SO4 aqueous, and we get Na2SO4 aqueous plus H2O. Now we balance, we did 2 and we did 2. All right, a nice hint for you guys. You notice that you've got two materials which are of +1 -1 charge. What I mean by that is +1 -1 +1, and you got 2 times that, but you've also got 2 negative. You've got 2 +1s, and you've got 1 minus 2, and you've got 2 times +1, and you've got 1 times -2. So what typically gets added, that 2 coefficient, is your ones with just 1s, this one, and your water. Okay, everything else stays as a coefficient 1 as such. All right, so there's another equation that we need to know in the back of our minds, is that what's actually the neutralization reaction? So we've got H plus OH minus gives you H2L liquid. So if we can find the moles of H plus and we can find the moles of our OH minus, we can compare and see if there's any limiting reagent. Compare that to find out N of our H2O. We can solve the question. So in this particular case, we have the moles of our hydrogen ions is 2 times the moles of our H2SO4. Why is that? Because we have a molar ratio of H2SO4 to H plus as 1 to 2. So every 1 mole of H2SO4 will give you 2 moles of H plus. So we have to assume 100% ionization of H2SO4. In reality, we know that doesn't happen. We know that the second ionization of H2SO4 is weak, but that's not something we need to worry about in this particular case. So that's just 2 times moles. You can calculate from C times V. So that's 0.12 liters times 0.5. Moles per liter, which is 2 times 0.12 moles. Our moles of OH is equal to the moles of our NaOH because of 1:1 molar ratio, NaOH to OH minus, which is just 0.06 liters times 0.5 moles per liter, which is 0.03 moles. So linking it back to this equation, we can say that since NH moles are greater than OH moles, H plus is in excess, OH is limiting, right? So we can then work out the moles of water because the moles of water will be dependent on the limiting reagent, which is our OH minus, which is 0.03 moles. Great, we've got that part. Now we just need to calculate our Q. Okay. Q, M, cat. M in this case, if it mentions density, we will use density, but if not, we would assume the density of 1. So we do 120 plus 60 mils as grams, density of 1, which means 120 plus 60 grams. But because I have the units of kilojoules per kilogram per Kelvin for my heat capacity of water, I will divide this by 1000 so that I get a kilojoules value. I get my heat capacity of water, kilojoules per kilograms per Kelvin, times the energy, the temperature change, which is 26.3 minus 24.2 Kelvin. Now, something to note, guys, is that you don't need to convert this value to Kelvin first, because the difference in Kelvin is the same as the difference in degrees Celsius. So they both act the same way. So what do we get in terms of a calculated value? 4.18 times 26.3 minus 24.2. 2.8524 kilojoules. Now, the purposes of me adding these units here is that I can go ahead and double check my work that I've used the right units. So I've got kilojoules, which cancels with my, sorry, I've got kilograms, which cancels with my kilograms here, and I've got Kelvin, which cancels with my Kelvin here. So what I'm left with is just kilojoules. Now, I'm not done yet. I've worked out Q, I've got N, I need to put them together to find my delta H. So my delta H equation is negative Q on N, and this Q is from there. The N is from the moles of water. So I do negative 2.8524 kilojoules over 0.03 moles, which is negative 95.08 kilojoules per mole. Okay. So any questions with that? Lovely. Let's move on. Now, another common question, the resultant pH of solution, sort of enthalpy as above, but not exactly. I can foresee that they could do a combination of these two questions. They could get you to calculate the enthalpy as well as get you to calculate the resulting pH. Might be a spin-off question. I've never seen those two questions linked together, but could be a possibility. Again, we start off with the equation. HSC4 plus KOH gives you K2SO4 aqueous plus H2O. So based on our previous quick trick, we do our 2 on the KO, H, and 2 on the water. Okay, next thing, we want to consider this equation again. So we want to consider what is our moles of our H plus and what is our moles of our OH minus. So it's pretty stock standard. That's the moles, that's 2 times the moles of our HSO4 because of 1 to 2 molar ratio, H2SO4 to our hydrogen. Therefore, that's 2 times 0.02 liters times 0.25 moles per liter, which is 0.01 moles. Moles of our OH is just moles of our KOH, 1 to 1 molar ratio. Whoop, not Na. Whoops. KOH. Scribble that. 2OH, which is 0.03 liters times 0.5 moles per liter, which is 0.015 moles. So once you've calculated those and you can compare limiting reagent, it makes your life so much easier rather than having you comparing H2SO4 and KOH as a 1 to 2 molar ratio. A lot of students struggle with that. So instead of comparing 1 to 2, we're comparing 1 to 1. So you can clearly see, okay, if my N of my H plus is 0.01 and my moles of my OH is 0.015, which one's bigger? Your OH is bigger. Therefore, OH is excess, H plus is limiting. So this is the only type of question we like to consider the excess because that's what's going to cause the pH change. So we need to consider excess N of OH, which is just 0.015 minus 0.01, which is 0.005 moles. Because a pH calculation involves this lovely equation, which is again on the data sheet, pH equals to negative log 10 hydrogen ion concentration. Yes, we want to do this. We want to work out the concentration of our OH minus, which is 0, which is N on V, which is 0.005 moles over our total volume, 0.05 liters. So that's going to equal 0.1. And if we do POH, which will equal to negative log to the base 10, 0.1, that will give you 1. And if you remember this relationship, pH is equal to 14 minus POH, or in other words, pH plus POH equals 14. then our pH is going to be equal to 13. pH has a slightly different sort of rounding. Instead of doing sig figs, we do decimal places, and the decimal places is equal to our sig figs. But instead of rounding to sig figs, we round to dp. So in this particular case, the numbers we've used are 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So we want to round to 3 dp. 3 dp is 1, 2, 3. 3 dp. Okay. All right. Now we get to the titration questions. So we want to start by writing out the equation again. So we've got nitric acid was determined using 1.01 moles per liter ammonium solution. A 25 aliquot portion of the ammonia solution was added to a conical flask, and a few drops of methyl orange were added. Excuse me. The titration took place with an endpoint giving a pale yellow color. The endpoints of 4 titrations are shown in the table. Lovely. So we get 4 titrations. This one, disregard. We will average these. Right. So let's start by writing the equation. Plus NH3 gives you NH4NO3. Cool. So they react in a 1-to-1 ratio. If they react in 1-to-1 ratio, we can use C1V1 equals to C2V2. Now, as a side note, if not 1-to-1 ratio, e.g. 1-to-2, 1-to-3, etc., we have to first calculate the moles of the known by using CV. Then we have to relate the moles of our unknown to moles of our known, and then use the unknown times the divide by the volume to get our concentration of our unknown. Okay, but we can use C1V1 equals to C2V2 in this particular case. So to denote it a little bit more clearer, we write C HNO3 volume HNO3 equals to concentration of our ammonia and volume of our ammonia. Now, concentration of our nitric acid is what we're trying to find. Lovely. We know the volume of HNO3, which is the average of these numbers. So that's just 0.0361. A hack, if these 3 numbers are consecutive and they differ by 0.1, pick the middle number. Saves you time calculating the average. Liters times concentration of ammonia is 1.01 moles per liter, times the volume, which was 25 mils. Now, our concentration should be in the units of moles per liter because we've cancelled these volumes around. So we want to move this one over, see what we get. Zero 0.699445 ... moles per liter. How many sig figs did we use? We used 3 sig fig here, 4 sig fig, 3 sig fig. So we use the lowest sig fig having the minimum being 2. So we use 3 sig fig, 0.699 moles per liter, 3 sig fig. Cool. Okay, this is not an acid and base titration specifically, but it's what we know as a back titration. Back titration involves a couple of things. So it involves us first reacting our unknown with a material. So our material is ammonium, reacts with our sodium hydroxide. The ammonium gas produced from this reaction reacts with, okay, so there's 3 reactions. Right, I'm just going to start at this. Ammonia. I'll explain why I'll start from there, and I don't need to worry about this. So we want to calculate the nitrogen composition, right? Ammonia also has nitrogen composition. So we react ammonia with hydrochloric acid. So our acid goes there. The excess hydrochloric acid, excess, HCl, so that goes there. This amount reacts with the ammonia. Don't know that much amount, but the excess then reacts with sodium hydroxide. So an equal portion of that, not to scale, reacts with HCl. So we've got these titer values below. Again, we can disregard the first one, rough titer. And we just average the 3 here. The average of the 3 is the middle one because they're differing by 0.1 from one another. So that's that one. So we want to write an equation first. HCl plus ammonia gives you ammonium chloride. Calculate the moles of sodium hydroxide used in the titration. Lovely. So as in this titration. So moles of sodium hydroxide used. So that's just CV, 2 moles per liter times the average titer, which is 0.0738 moles. Because this is the final answer, we need to make sure we're rounding it to the correct significant figures. 33333, just 3. So 3 sig figs, it's already in 3 sig figs. Perfect. Calculate the percentage of nitrogen per mass, by mass. Okay, so we've got the moles of sodium hydroxide in the titration. We can find out the moles of our HCl excess, which is a 1-to-1 molar ratio with our NaOH, because molar ratio from this reaction. Beautiful, which is the same. Now the beauty of back titration questions are they're pretty straightforward once you get to know them. So you've got the excess, got we've got this. We know the initial amount of HCl we've used. Because we know that, we can work out the difference of your initial HCl and your excess HCl to find what's actually been reacted. So let's go and work that out. So HCl initial is equal to, you've initially used 50 mils of 2 moles per liter. 50 mils times 2 liter, 2 moles per liter, which is 0.1 moles. If we do the difference, i.e. the moles of HCl initial minus moles of HCl excess, we can determine the moles of HCl reacted, which in this case is 0.1 moles minus 0.0738 moles, which is 0.026262 moles. So we've got that moles. Oops. Then we go back and see, okay, bit of lag. Is it going to act up? Then we compare the moles of our HCl reacted with moles of ammonia. We know from our part A, it's 1 to 1. Part A. Therefore, moles of ammonia is also equal to 0.0262 moles. Nearly there. So, you can see the amount of N's in your ammonia and your ammonium sulfate, is 2 times, or it's half of what's actually of your ammonium produced. Yes, so we want to relate our ammonia with our nitrogen. But that's just 1-to-1 ratio, because for every 1 mole of ammonia, there's 1 nitrogen available. So we then can say the moles of nitrogen is equal to that, because again, 1-to-1 molar ratio. Great. So we can then work out the mass of our nitrogen, which is nitrogen moles times molar mass, which is 0.0262 moles times 14.01 grams per mole, which is equal to 0.367062 grams. And then to calculate percentage mass, or what we call weight per weight, we do mass of nitrogen over our total mass. So that's going to be 0.367062 grams over 1.746 grams times 100%, which is equal to 21.023%, which is, to the right sig figs, oh, why is it lagging like that? we've used 3 sig figs, 3 sig figs, 3 sig figs, 4 sig figs. So we want to just do 3 sig fig, 21%, 3 sig figs. Okay. All right. These are long-winded questions, but if you follow one step at a time, is it lagging because I have autosave on? Maybe. All right. So, lagging even more now. So back titrations involve a couple of steps. You initially working out your NaOH moles in this particular context, NaOH moles, working out your excess HCl that you've used. You want to work out your initial, which is your third step. Do the difference to find what's reacted, and then compare what's reacted to your targeted molecule or chemical. And then the additional thing with back titration is if they tell you to find the mass, which is more of a Mod 8 question, where you do gravimetric analysis, but that forms the basis of your back titration. Okay. Next question. A sample of impure sodium carbonate required 24.65 mils of HCl solution for titration. A 0.2204 gram sample of pure sodium carbonate required 20.06 mils of HCl solution of the same concentration. Calculate the mass of sodium carbonate in the impure sample. Include a balanced equation in your answer. Okay, balanced equation, so easy. Just make the sodium carbonate with HCl. So what are we trying to find here? We're trying to find the mass of sodium carbonate in your impure sample. Does the impure sample contain anything else that might affect the titration? Let's just say, assuming no further impurities in impure sodium carbonate solution. No, assuming no further impurities impure will affect titration. So what I mean is only sodium carbonate in impure sample will react with HCl. Okay, so from the looks of things, you need to first find the concentration of this HCl and then go back and do this step. So we can do that. We know the moles of sodium carbonate. Sorry, before we do that, let's do our balanced equation. Na2CO3 solid plus HCl aqueous plus gives you NaCl aqueous H2O plus carbon dioxide. So 2 there, 2 there. Now we want to work out the moles of our Na2CO3, which is 0.2204 grams over 22.99 times 2 plus 12.01 plus 6, not 6, plus 3 times 16, which gives you 0.00207944 moles. And if we relate the moles of our Na2CO3 with our moles of our HCl, that's 1 to 2, because molar ratio. Therefore, the moles of our HCl is sorry, mind blank, brain farted, 0.00, sorry, it will be 2 times N of Na2CO3, which is 0.4158888291 moles. Now we can find the concentration of HCl using N over V, which is that number. Oops, sorry, that's an 8. Over volume, which is 0.02006 liters, which ends up being 0.0207322171 moles per liter. So that's the concentration, and we've used that concentration to find the impure sodium carbonate. So basically we're doing the reverse now. So we're trying to find the moles of HCl reacted in impure with impure, which is C times V, which is 0.02073 moles per liter times 24 mils, which is 0.02465 liters. 0.000511049117 moles. And again, what happened? Drag this back in place. Okay. That's some more lines. So we can then say HCl ... the moles of Na2CO3 is 2 to 1. Therefore, the moles of Na2CO3 is equal to half the moles of HCl, which is half the number of that. Which is I'm going to write scientific notation now. It's getting a bit too small. 2.555458 times 10 to the negative 4 moles. Moles. How to get to mass from moles? This is the impure Na2CO3 moles. We do mass. Molar mass times moles, which is 22.99 plus 12.01 plus 16.3 times that number. Which is 0.02708,305 grams, which is 4 sig fig, 4 sig fig, 4 sig fig. So we do 4 sig fig, 0.02708 grams for sig fig. Great. Now, I always like to double check. That doesn't seem right. 27. I am off by a 24. So the reason why I've checked that it's wrong is because I have my initial mass, which is 0.2204, and I've used 20 mils for that, but I've used 24.65 mils of the same solution, and I've ended up with a smaller mass. So let's see what went wrong. This is a perfect example to see what happened. So let's type in our numbers again. We've got all our working out there. So all we need to do is put them all in there again. Yep, that's the same one for moles. So we're saying that 2 times should be 2 times. Yep. And then we're doing n over v to get concentration, divide by 0.02006 to give you, this is where we typed in wrong. So that's wrong. So that should be just 0.20732 moles per liter. So that means we just need to update everything else. That should be that. That should be that. We're just crossing off 10 just before the decimal point. That's an easy fix. So instead of that being 4, that should be 3, negative. And that should be not there. That should be not there. That should be our answer. Now that makes more sense because the mass should be slightly bigger than our 0.2207 or 04. Should be of the same magnitude because we're requiring the volume of the same magnitude. So that makes more sense there. Okay. So not on purpose, but shows how important it is to write all your working out from top to bottom, and then you can work out where you got that mistake and potentially fix it much with less time than you might if you didn't have all your working out there. Okay, so that's all the working out there. All right, this is our KB questions. So these are your acid dissociation. Oh. Questions? Again, we want to start off writing our equation. So it tells us how it reacts. Is it a base? Is it an acid? As such. So it says hydrazine N2H4 is a common rocket fuel spandex suits. It's common to rocket fuel spandex suits, power stations, and car airbags. Like ammonia, it is classified as a Bronsted-Lowry base when it reacts with water. A 0.5 moles per liter solution has a pH of 10.7. Calculate the Kb for hydrazine. So it says it's a Bronsted-Lowry base, which makes things lovely. So let's just say this is aqueous because it says a solution. So reacts with water and is a base. So because a base is a proton acceptor, we can write hydrazine as N2H5 plus aqueous plus OH. Why it's OH? Water acts as a Bronsted-Lowry acid in this case, so it proton donates to the base, resulting in an OH. Now, to write our Kb solution expression, my apologies, is we do the same thing as our KQ, KSP, products over reactants. So we do products over reactants. And again, these are at equilibrium. Now, the values we've got is we've got a solution concentration, we've got a pH. Now, we can work with those two numbers to get what we want. So first thing I like to always do is I like to make this assumption. Assume this equilibrium concentration is the same as the initial, as N2H4 is a weak base, meaning it has low dissociation. Now, you might think, how do I know that? You can assume, or if you feel like really calculating, this is a weak base because for pH to have that, we can work out the pOH. I'll prove it in the subsequent stage. So that means that's equal to 0.15. So going on the pOH situation, our pOH is equal to 14 minus pH, which is 14 minus 10.07. 10.7, sorry. 3.3. For a solution of 1.5 moles per liter of hydrazine, we should expect, this is a side note, and it gives off 1 mole of OH, we should expect the pOH to be negative log that, which is negative log but you can see the discrepancy between 3.3 and 0.823. So this is assuming 100% dissociation, meaning strong. Any number that's more than that, as in the pH value is greater, means there's less dissociation. So we can justify that assumption by having pOH not equaling 0.8239. Okay, so on that note, we can find the hydrogen ion, sorry, not hydrogen ion, my apologies, hydroxide ion concentration by doing 10 to the power of negative pOH, which is 10 to the power of negative 3.3, negative, scientific notation 5.01187 times 10 to the negative 4 moles per liter. So we've got that concentration of, we've got this one, we've got this one, we need this one. How do we justify that? We can justify by saying that's also equal to your N2H5 plus at equilibrium as 1:1 molar ratio. What that essentially means is that for every 1 mole of for every mole of OH produced, you're going to get 1 mole of N2H5 plus. Okay? So, do I have enough space? I might. We can try. Kb is equal to 5.01187 times 10 to the negative 4 times the same thing over N2H4, which is 0.15. That's equal to 1.67459094, sorry, times 10 to negative 6. No units, but we then round that to 2 sig figs, 4 sig figs, 2 sig figs. This isn't a pH calculation, so we just still round to the sig figs. So that's 2 sig figs, so that's 1.7 times 10 to the negative 6. 2 sig figs. Okay. Hope everyone's doing all right. No questions so far? All right. To maintain the pH of a swimming pool, hypochlorous acid HOCl is added. This acid ionizes into hydronium ions and hypochlorite ions. The pKa of HOCl is 7.3. Calculate the pH of a 0.1 mole solution of hypochlorous acid. Okay, so great. So if you haven't noticed already, there are 3 things which form a triangle with one another. So we've got Ka, pH, and then we've got acid concentration. So these three things play a part in determining one out of the three, assuming that we know two of them. So let's say if we know the concentration of our acid, if we know the concentration, if we know the Ka value, we can work out the pH. If we know the pH concentration of the acid, we can work out the Ka value. You typically don't work out the acid concentration that you've used, because that's what you typically know from a laboratory point of view. You know what acid concentration you use, but you might sometimes need to work it out. This triangle forms the three things that the two out of the three things that you need to work out the third one. Okay, remember this relationship. That will constitute all your Ka questions. A revolution, knowing two, working out the third. So in this case, we know our pH. We know our, we don't know our pH, but we know our Ka, and we know our acid concentration. So we know our Ka through our pKa. We can work out what the pKa is. Let's start with the equation, as always, right? So we do hypochlorous acid you can write that, or you can react it with water, and then you produce hydronium ions instead of H+. Let's do our Ka expression. Hydrogen ions, OCl minus HOCl, which is equal to 10 to the power of negative 7.3. pKa is just negative log to the power of Ka. That's on your data sheet. It's the same conversion when you find the other way around. It's the same as your pH, same as your pOH. So let's try to find out what our pH is. So pH is just H+. H+ is also equal to our OCl minus. So we need to assume again, HOCl is weak and has low dissociation. Therefore, these are all equilibriums again. Therefore, HOCl equilibrium is equal to our HOCl initial, which is equal to 0.01. And we can say H plus equals to OCl minus 1:1 molar ratio. Therefore, we can rearrange and say H plus squared over 0.01 is equal to that. H plus is equal to square root 0.01 times 10 to negative power of negative 7.3. Which is equal to 2.23872 times 10 to the negative 5. This is moles per liter. Then we can say pH is equal to negative log hydrogen ion concentration, which is negative log of the answer, which is 4.6. Now we've used 2 sig figs, 1 sig fig. Still, we use 2 dp because that's the lowest significant figure there. Surprisingly, it's a nice number like that. They must have worked out the other way for the question. Anyway, that's that. Okay, we've got 2 more questions for acid and base, and then we get into mod 7. Okay, I think these are quite honestly the easier ones. So again, we got the trinity of got the Ka, pH, and acid concentration. In this case, we are trying to find POH, so it's equivalent of this. We know Ka, we know the concentration of acid. Okay, I'm going to speed through these ones because I feel like I'm a bit slow today. So we just worry about 1 degree of ionization in this particular case. So our Ka is equal to hydrogen ion concentration times the concentration of our hydrogen carbonate over our carbonic acid, which is equal to 4.3 times 10 to the negative 7. And we can make those two assumptions again. Our equilibrium concentration of our carbonic acid is equal to our initial concentration of our carbonic acid because of H2CO3 is weak and has low dissociation. And then the second assumption we can make is hydrogen ion concentration is equal to hydrogen carbonate concentration because of 1-to-1 molar ratio. Therefore, we can say hydrogen ion concentration squared over 0.2 is equal to 4.3 times 10 to the negative 7, rearranging H plus concentration equaling square root of 0.2 times 4.3 times 10 to the negative 7, which is equal to 2.932575 times 10 to the negative 4 moles per liter. pH is equal to negative log 10 hydrogen ion concentration. Now we can find pH first, or we can find the hydroxide ion concentration. So we can relate this relationship. This assumes 25 degrees. Yes. So you would rearrange, you know this, you push that over there, and you get your hydroxide ion concentration. But unlike that, I think that you're dealing with too many numbers. This way might be easier, personally. So we do that. That equals to 3.53275 ... POH is 14 minus pH, which is 14 minus 3.53275 ... which is 10.4672 ... And we note that we're using two significant figures there. So we do 2 dp. So 10.472 dp. POH has no units, so we just leave it like that. Okay. Butanoic acid is a natural product and a component of human sweat. Calculate the Ka value. Excuse me. Calculate the value of Ka for butanoic acid if 0.10 mole per liter solution has a pH of 2.9 at 298 Kelvin. All right. You need to know what butanoic acid is. So the formula is C4H10, and I like to, oops, what's going on? I like to say C4H, no, not C4H, okay. Now we have to draw it. So C48, COO. What am I doing? C4H7. Okay, what's going on? Okay. That should be a double-headed arrow. Gives you C4H7COO minus plus H plus. Ka C4H7COO minus H plus
C4H7COOH. That's equal to, I know, that's what you're trying to find. We have to say that this is equal to our initial. (0.1) because of weak acid having low dissociation. And then also pH, 10 to the power of negative pH equals to hydrogen ion concentration, which is 10 to the power of negative 2.9, which is also equal to the concentration of C4H7COO minus because of 1:1 molar ratio. So Ka is equal to 10 to the power of negative 2.9 squared over 0.1. 10 to the power of negative 2.9 whole squared over 0.1. That is equal to 1.584893 times 10 to the negative 5, which in this case is 2 sig figue. 1.6 times 10 to the negative 5. 2 sig figue.
Great. This is all Mod 6 questions. Quick drink break. Anyone have any questions so far? Okay, if not, let's keep going. We get to our enthalpy questions for enthalpy of combustion questions. So this is the hint, or this is the tip for you guys. There's two equations, and there's two sections. So you can't get this wrong, unless you write the equations in a different way. So this N talks about the N of the fuel. Contrary to what we did in our acid and base neutralization, that's water. This one is fuel, okay? Don't get that mistaken. This mass is the mass of water, not the mass of the fuel. Everything else is the same. Balance equation for the complete combustion of heptan-1-ol. So, heptan-1-ol, C7H. It's 2N plus 2 for your alkanes. And we're just removing one of the H's and replacing it with an OH. So, O15, OH. And heptamonol, let's just say liquid, O2, gas, gives you CO2 plus water. This is for complete combustion. If you get incomplete, you could get CO, water, or C with water. Pick one and balance your equation. You have every right to write that down unless they specify what products you get. Otherwise, if you do a mixture of CO2, CO, C, you'll be heat balancing it forever. So just pick one of those and balance away. Okay, let's do Q equals to MCAT. So our mass is the mass of water, 150 grams. And I like to change that to kilograms because of my C that I'll be using. 4.18 kilojoules per kilograms per Kelvin times temperature change. So we've got 63 minus 20, which is 26.961 kilojoules. Our moles of our fuel is mass over molar mass. 0.75 grams over the molar mass of heptanol. 7 plus 16 times 1.001 plus 16. 1 times 7 plus 16 times 1
So 1 plus 16. 0.0064540 moles. Delta H equals to negative Q on N, negative 26.961 kilojoules per 0.0064545 moles, which is equal to negative 26.961 over answer is negative 4177.085704 kilojoules per mole. Something to note, we always have enthalpy in kilojoules per mole. So to round that value to 3, 3, 4, 3 sig figs. So negative 4180 kilojoules per mole, 3 sig figs. Okay. All right. There's not a lot of calculations in Mod 7, more memory based. So we've done one basically in the second inquiry questions of alcohols, and then the subsequent ones are in the sixth inquiry question, which is polymers. So we've got a monomer unit, which forms a polymer containing, this monomer forms a polymer unit containing 1000 monomers of those units. The approximate molar mass of this polymer. So general formula you can follow is monomer times number of units gives you polymer, approximately. Reason is, this is a condensation polymer, and for every monomer there is, we have to take away 18 for precise calculation. For this, we won't worry about it. Let's see what we get first. So let's calculate the molar mass of our monomer times the number of units, which is 1000, to give us the molar mass of our polymer, which is what we're trying to find here. Sorry, I was writing in red. So molar mass of our monomer is 12.01 times 3 plus 1, 4, 16 times 1, 3, and then 1.008 times 1, 7, 8. So that equals 104.101, and we want to times that one by 1000 to get the polymer. So that's 104 times 10 to the 5, which is approximately D. Now we reverse for the next question. We do same thing, monomer times number of units equals polymer, approximately. And we want to say how many units there are. So we just do polymer over monomer equals number of units. So our monomer is this. This is an addition polymer. So all of your atoms will stay in your polymer. So how we denote this is as follows. Where N is the number of units. Okay, so we know the polymer's molar mass. We know the monomers, we know the polymer's molar mass. We know the monomer's molar mass, which is 12.01 times 2 plus 19 times 4, which is 12.01 times 2 plus 19 times 4, which is equal to 189.962 dot, 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 which is approximately equal to 190. So A. Okay. That's all the Mod 7 questions. And I've just had another realization. Okay. Couple more pages to go. Okay, let's start with this one. This is a gravimetric analysis question. So we're trying to use the weight of precipitate to backtrack concentration. So in this case, the sulfate content of a fertilizer was measured by dissolving 1.63 grams of fertilizer in 300 mils of water, then slowly adding a solution of barium chloride until no further precipitation occurred. After filtration and drying the mass of the precipitate, filtering and drying, the mass of the precipitate was 1.81 grams. Calculate the percentage of sulfate in the fertilizer. So what we're trying to do is we're trying to do barium plus sulfate gives you barium sulfate, basically. And that's the precipitate. So we can try to find the moles of our barium sulfate, which is 1.8 grams over barium sulfate. Barium's molecular mass is 137.3 plus sulfate, which is 32.7 plus 16 times 4. Zero 0.007755 moles, and we can relate that moles to the moles of sulfate, which is 1 to 1 because of molar ratio. Then we can go back and work out the mass of our sulfate, which is timesing it by the molar mass. Which is 32.07 plus 16 times 4. Which is 0.745116253 grams. Now to calculate the percentage of sulfate, that's typically weight per weight. That's going to be equal to your mass of sulfate over your total mass, which is 0.745116253 over total mass. And we're going to times that by 100%, which is 45.71236 ... which is 45.36 figs, 45.7%, 36 figs. Cool. All right. Next question. The percentage of sodium chloride in food can be determined as follows. Completely dissolve the food sample using an appropriate solvent. Add excess sodium nitrate solution to the dissolved food sample to precipitate all chloride ions. Wash and dry the resulting precipitate. Okay, so the precipitate in this case is AgCl. So the moles of AgCl is 0.396 over silver is 107.9 plus 35.45. Zero 0.002764 to the dot, and we can relate that to our Cl. Ditto and we do mass of Cl, which is 0.00276 times 35.45, 0.0979 to 9 grams, and we could do a percentage. Sorry, that should be Cl, which is equal to the moles of NaCl. So we shouldn't times that by that. We should times that by 22.99 plus 35. Okay, so we take that value, 22.99 plus 35.45, 0.161438. Percentage is equal to 0.161438 over 0. Okay. Yes, not 0. 22. We want to times that by 100%. That's going to equal 0.73381% which is closest to B. Cool. Okay. Now we're trying to find the purity, and it looks like this is a anhydrous 2 grams of anhydrous sodium carbonate was added to a small amount of barium sulfate. To determine the purity, the 2-gram solution was transferred to a clean conical flask. 25 mils of distilled water was added, producing that slightly white, opaque methyl orange. The mixture was was titrated against standardized that. So it has a small mass of barium sulfate. So barium sulfate is producing the slightly white, opaque because it's insoluble. So it looks like HCl reacts with sodium bicarbonate to give you salt, water, CO2. Now we have to assume barium sulfate is inert. What inert means is it's not reactive. And does not participate in titration. All right, so we can say N of HCl is equal to C times V, 1.5 moles per liter times 0.01575 liters, 0.023625 moles. And we can say the moles of your sodium carbonate, the moles of our HCl is 1:2, molar ratio. Therefore, moles of HCl, the moles of sodium carbonate is equal to 2 times 0.023625 moles. And then yes, that's equal to 0.04725 moles. And find the mass of Na2CO3 by doing that by the molar mass times 22.99 times 2, 12.01 plus 3 times 16. 5.008275. Again, that doesn't look right, hey? No, it does not participate. Yeah. So 1.5. Yeah. Times 2 gives you that. Times 22.99 times 2 plus 12.01 plus 5. Very interesting. Huh. That's the mass. Oh, yes, yes, yes. Yes, yes, yes. The molar ratio is incorrect. Sorry, it is incorrect. It is correct, but I need to halve that. Yes, halve that instead of. So that should be 0.0118125. 0.0118125, and that should be 1.252006875 grams. And we do percentage weight per weight, 1.252006875 over 2 times 100%. 62.60034 which is 3 sig fig, 3 sig fig. 62.6%, 3 sig fig. Okay, pretty good with time. Okay, another precipitation titration. So we've got 100 mils of solution is said to contain iodide ions. To determine the concentration of iodide in the solution, the following investigation was conducted by a student. It was added so that all the ions would precipitate. The precipitate was filtered, separated from the final solution. The excess silver ions in the final solution was titrated with potassium thiocyanate using iron 3 ion as an indicator. 35.14 mils of potassium thiocyanate was required to reach the endpoint. Okay, so when we see excess, we want to associate back titration. Excuse me. The burette was filled with thiocyanate solution. Identify what the burette was rinsed with prior to filling. So we should rinse with the thiocyanate solution. The thiocyanate solution. Okay. Determine the concentration of iodide ions in the original solution. So, because this is a back titration question, we want to work backwards. So we want to say the before we can determine that, we need to say Ag plus SCN gives you AgSCN. So it reacts in a 1-to-1 ratio. So moles of SCN is equal to moles of Ag plus excess. This excess is relative to the back titration, which is equal to 0.05322 moles per liter times the volume, 0.05322 times 0.054, 1.870158 times 10 to the negative 3 moles. We know our initial Ag plus initial moles, which is 0.05 liters times 0.05619 moles per liter, which is 2.8095 times 10 to the negative moles. So Ag reacted is our initial minus our excess, which is 2.8095 minus 1.870158 times 10 to the negative 3 moles. 701,508. That's going to equal 9.393492 times 10 to the negative 4 moles. Yep, that's good. And in respect to our iodide ions, so Ag plus iodide ions, Ag iodide, moles of our I is equal to moles of our Ag reacted, which is 9.393492 times 10 to the negative 4 moles, which in respect to a concentration, that's N on V, 9.393492 times 10 to the negative 4 moles over the volume, $100 mils, 100 mils. Which is 9.3934 times 10 to the negative 3 moles, which is 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So we use 9.39 times 10 to the negative 3 moles. 3 sig figs. Ooh. Two more. And hopefully have some time to go through the other ones as well. Okay, so after further analysis, it was determined the unknown compound was iron. To determine the concentration of iron ions, AAS was used. So we're going to mod 8 now. Soup samples were prepared in the following manner. An excess of sodium carbonate solution was added to exactly 2.5 grams of the soup sample. An iron precipitate formed. That would be iron 2 CO, iron 2 plus. It's filtered, washed, and dissolved in a few drops of hydrochloric acid. The solution was diluted to exactly 25 mils. This sample was analyzed using atomic absorption spectrometry. Standard solution shown below. Okay, great. The treated soup sample had an absorption of 4,500 Okay, so first thing, we want to draw a straight line with a ruler. So that's there, and that's there, approximately speaking. So I would say that might be 190 micrograms. Yes, and that's per 25 mils. Okay. So we know that this solution was diluted to 25 mils. We can then say in the solution 25 mils, 190 micrograms of Fe2 plus is present. Now we want it to ppm. ppm is parts per million. You can either represent it as a weight per weight, or it could be a weight per volume. So it could be milligrams per kilograms as a weight per weight, or it could be milligrams per liter as a weight per volume. So we want to do weight per weight because we've got a weight here of Fe2 plus, and then we've also got a 2.5 grams of a soup sample. But we've got our concentration in micrograms at the moment. So how we do this is we just do milligrams, kilograms. We want to convert the top by dividing by 1000, but we also want to divide the bottom by 1000. So that will just be grams. So micrograms to grams, that's all we need. So in ppm, or concentration of Fe2 plus in soup, that's just 190 micrograms over 2.5 grams of soup. That's just 76 ppm. And how many significant figures did we have? We had 3, so that's 76.036 fig. Pretty straightforward for that one. All right. Last question. Hopefully we have some time to go through some of the ones that were missing from this slide. Colorimeter was used to calculate the percentage of iron, 0.2 grams. Tablet was oxidized and dissolved and oxidized and reacted with disulfate. The resulting solution was made up to 200 mils, and the final absorption was 0.6105. Okay, how much iron was in the tablet? So I see a calibration curve. It's given me a equation, which will be very helpful because I can just sub in the absorption. Let's do that first. 0.6105 is equal to 0.0111x. X is your concentration of Fe3 plus. That's just 0.6105 divided by 0.0111. That's just 55. And that's in micromoles per liter. Okay, now we work with the 200 mils. So we times this by 200 mils, which is 11 micromoles. It's 0.2 grams tablet, irrelevant. We're not finding concentration. So times that by 55.85 grams per mole. That's just 14.35 micrograms. Micrograms is 10 to the negative 6. So if we do that to scientific notation, that's just 6.1435 times 10 to the negative 4 grams, which will be C. All right, let's have a look for some other questions that we are missing. So while we're on Mod 8,
Okay. Okay. Another calculation question I missed is B. Lambert. Okay. So this is where we use B. Lambert's equation, which is also in your data sheet, which is this one. A equals to epsilon length times concentration equals to log base 10 of your incident rate over your absorption of your detected length. So A is equal to epsilon times concentration times length is equal to log 10 of your incident ray over your detected wavelength or intensity. So we have a spectroscopy was used to determine the unknown concentration of copper-2 sulfate in a solution. The intensity of light produced by the spectrophotometer was 10.6, but after being passed through a 1 centimeter cuvette, the recorded intensity was only 2.1. The molar absorptivity, which is your epsilon, of the sample was known to be 49,650 liters per centimeter per mole. Using the B. Lambert's law, what is the concentration of copper-2 sulfate in the sample? So we just need to determine concentration, which is this guy. We know everything else. So we know epsilon is 49,650,000 liters per centimeter per mole. And we want to times that by the concentration, which is unknown. We know the length. Length is 1 centimeter is equal to log 10. The intensity of the original ray, which is 10.6, over the recorded intensity, which is 2.1. Now, this number, from your maths knowledge, logs must be greater than 0. Specifically greater than 1 if it's base 10. Otherwise, it's negative. So if you have log, you have a negative value. Don't know if you saw that. But so what that means is the number on the top must be greater than the number on the bottom. So this must be the original. This must be the recorded or the detected one. Okay? So if we move everything to the one side, the concentration should be moles per liter, first of all, because we do moles per liter. So moving everything to one side, we've got 4965, which is 1.416085 times 10 to the negative 5 moles per liter, which is D. Okay, that's as hard as it gets. You're revolving around finding the unknowns here. They'll give you all your unknowns except for one. So they'll give everything as known values except for one unknown, and you need to work out the rest. Very rare do they give you an absorption value. The absorption value gets derived from this anyways, this side. So that's that. Okay, I'm going to go back and do Gibbs free energy. Hopefully I can find one within the next 20 minutes. I'm sure I'll find one. And then also a common ion effect question. free energy, gives free energy. Okay. Okay. Let's do this one. This looks like a nice question to do. Oops. That's acid. Oh, there we go. Okay. This is a Gibbs free energy question. So your typical question looks like that. You have an equilibrium system that you get given enthalpy of formation data for your reactants and products, as well as entropy data for reactants and products. They've separated out the question into the different parts. That's exactly what you need to work out. A to B. A and B are typical steps that you need to work out in order to determine Gibbs free energy. So let's do that. So your enthalpy change will be equal to your sum of your enthalpy formation of your products minus the sum of your enthalpy of formation of your reactants. So that's based on your coefficients. So they're all 1, 1, 1, 1. So we can just add all of them in your products minus the summation of your reactants. So your products are negative 393 minus negative 111 minus 242, which equals to negative 40, and that's kilojoules per mole. They have it in 3 sig figs, so let's have that in 3 sig figs. Enthalpy change, again, very similar. Replace the H with a S. So that's 214 plus 131 minus 198 minus plus 189. 214 plus 131 minus 198 plus 189. Negative 42 kilojoules. Oh, sorry, not kilojoules. What are the units there? The units there are joules per Kelvin per mole. Now, to determine if something is spontaneous or not, we need to consider delta H, delta G. Delta G again is given in your data sheet, and it's given as delta H minus T, temperature, times your entropy. Now, the units for these types of questions are very important. We want to have temperature in Kelvin. And note, entropy units is joules per Kelvin per mole. We need to manipulate the entropy value divided by 1000 in order to get a value in the units of kilojoules per mole, which we will get. So let's put the numbers all in. I like to put in the units as well, just to make sure we don't forget to divide by 1000 from what I just said. So our temperature is is 600 Kelvin times entropy. Entropy calculated value is negative 42 joules per Kelvin per mole. So what we end up getting, now I need to divide this one by 1000 so that I can say that's a kJ. Negative 40 times, minus 600 times 42 divided by 1000. That's negative 65.2 kilojoules. Because this is negative, therefore reaction at 600 Kelvin
is spontaneous. Now, Gibbs free energy is temperature dependent. It could be unreactive at a lower temperature. You need to calculate that based on this equation. So if delta G is negative, spontaneous. Delta G is greater than 0, not spontaneous. And if delta G is equal to 0, then we have an equilibrium. Okay? Given that when a reaction has reached equilibrium, delta G equals to 0, calculate the minimum temperature required for this reaction to reach equilibrium, understand the conditions, and state when the reaction will be spontaneous. Okay, so in order to do that, we need to say delta G equals to 0 equals to delta H minus T. That. So T, in order to work out T at 0, that's going to be delta H over delta S. That's going to be negative 40 over negative 40, but we want to divide this one by 1000. Okay, well that's gone wrong. Right, so 952.38095 which is 3 sig figs. 952 Kelvin is minimum temperature to reach equilibrium, and state when the reaction will be spontaneous. Huh, but that's something wrong. Negative 42. So, for the reaction to be spontaneous, delta G needs to be less than 0. So, for that to be less than 0, that has to be less than 0. And if we do moving around, delta, the temperature must be less than 952. So in order for spontaneity, T must be less than 952 Kelvin. Okay, great. And there was only one more question that we hadn't gone through, which was the common ion effect. Common ion. All right, this is a good example, I reckon. All right, last example. This one is a common ion effect. We'll demonstrate by an example, but essentially, if there are ions already in solution which forms the base of your salt, as in either your cation or anion, then the solubility will decrease because there's already ions in there. That's going to increase the amount, that's going to accelerate the amount of salt that's going to become solubilized and then reach saturation, meaning that any extra salt will be a precipitate. Okay, so lead chloride is sparingly soluble in water, and an equilibrium is established between the solid and its ions in solution. Calculate the concentration Pb2 plus and Cl minus in solution. Great. Okay, so we first start off with an equation. So our KSP value is Pb2 plus Cl minus squared. So from our knowledge, because we have that, it's going to be S times 2S, squared, which is 4S cubed. And that's going to equal to lead chloride 1.7 times 10 to the negative 5. S is going to equal 1.7 times 10 to the negative 5 over 4. And we're going to do the cube root of that. So the cube root of that is, oops, sorry, that's cube root of 1.7 times 5. 1.7 times. That's going to equal 0.016198 moles per liter. And KSP is given in 3 sig figs, so let's do 3 sig figs. 0.162 moles per liter. 3 sig fig. All right, B. Calculate and compare the molar solubility of lead chloride when dissolved in 0.25 moles per liter of NaCl. So this is where we have to consider an ice table because our initial concentrations have changed. So 1, 2, our initial for Pb is 0 because our salt hasn't solubilized yet, but our Cl has become 0.25. Our change is still plus air, let's do S. And then this would be minus 2S. S, negative 0.25 minus 2S, plus 2S. So our KSP expression is still the same. But instead of them being S squared, 4S cubed, it's 0.25 plus 2S squared. Now, we can assume that is equal to just this, as S is less than due to lead chloride being sparingly soluble. What that means is that when lead chloride solubilizes, in comparison to 0.25 moles per liter of chloride, it's very, very small. So we'll find that S is very insignificant, several orders of magnitude smaller than 0.25, which allows us to make this assumption. We can verify that. So by having that equal to just 0.25, we can simplify the KSP calculation to just this, and then S is just equal to (6.8) times 10 to the negative 5, which, if I was to express it in a decimal place, 0.000068 moles per liter. And for 3 sig figs, that. And now the comparing gives marks as well. So we can say when there is a common ion, the solubility of the salt significantly decreases. And that's it.
And we are 7 minutes early. Let's see if we have any questions. No questions. I guess we can wrap it up here. I hope everyone's learnt something today. For those who are watching this, if you have any questions, feel free to leave them in the comment section below, and I will attend to every comment. You can ask me about any chemistry questions, and I can give you a hand with that. But otherwise, thanks for watching, guys. If you like the content, show some support. Let me know what other videos you'd like me to make. But I intend on having several more of these before HSC, focusing on more frequently asked HSC questions. I know no one's here, but I'm just going to show it anyways. There are statistics of what types of questions HSC has been asking. I would like to show you that for those who are actually watching. So, where are my calculations? So, your top question is your spectroscopy for your organic compounds. Second top question, titrations with acid and base. Third question is your spectroscopy with your inorganics. Fourth top question is your KSP values. Fifth question is your LCP. Now, for those who actually watched till the end, here it is. Here's a gift. Here's a gift from me. But yeah, that's all. That's all for me. I will catch you guys next time. Thank you for watching.